name is Caitlin Raby. I will be speaking to you about sonomyography as an input for control of powered lower limb assistive devices. More than 1.9 individuals in the United States live with the loss of a limb, and 90% of new amputations involve the lower limb. While assistive device technology has improved immensely in the past decade with the introduction of powered assistive devices, the sensing and control interfaces of these devices do not allow users to access all of the high-level features outside of the lab. A critical gap remains, and there is a need for a non-invasive human-machine interface with the ability to sense user intent and replicate the motion of a healthy limb. This is reliant on accurate and continuous sensing of user motion. Sonomyography is the evaluation of real-time dynamic ultrasound imaging of skeletal muscle and can be used to quantify measures of skeletal muscle architectures such as muscle thickness, pennation angle, and fascicle length. Additional features of sonomyography are the overall image brightness as well as the brightness of each element of the image. All of these features have been previously correlated with the onset of muscle contraction, muscle force production, and resulting joint motion. We hypothesize that sonomyography has the potential to predict several different inputs relevant to various device control architectures. There are multiple types of ultrasound sensors, including A-mode ultrasound, which gives an amplitude signal from single ultrasound elements, as well as B-mode ultrasound, which results in a grayscale image reconstructed from a linear array of ultrasound elements. For the purpose of this presentation, we will focus on results from features extracted from B-mode imaging only. The first experiment we completed was the continuous prediction of ambulation mode. We collected data from 10 able-bodied subjects equipped with a 128-element linear array transducer placed transversely on the anterior thigh to collect ultrasound images of the vastus medialis, rectus femoris, and vastus intermedius muscles. Subjects were asked to complete 5 ambulation tasks, and ultrasound intensity features were extracted from the continuous stream of ultrasound images collected during these tasks. The ultrasound intensity features consisted of mean image intensity extracted from 3x3 millimeter blocks of the ultrasound image ranging from superficial to deep muscle tissue. Overall classification accuracy of ultrasound sensing using a linear discriminant analysis classifier was 99.8%, with 100% accuracy for level, incline, and decline walking tasks and 97.6% accuracy for stair ascent and stair descent tasks. In order to determine where in the gait cycle these misclassifications were occurring, we plotted classification accuracy as a function of the gait cycle. And you can see that in both stair ascent and stair descent, the most misclassifications occurred at the beginning of the stride, and as the stride progressed, the classification accuracy improved. After we predicted the ambulation mode, we turned to look at continuous prediction of joint moment. We used the same data set and ultrasound intensity features as before to predict hip, knee, and ankle joint moments during level, incline, and decline walking tasks. The greatest percent errors from the Gaussian processes regression model were seen at the ankle due to imaging muscles that do not span the ankle joint. However, less than 10% root mean square error was reported for all walking tasks of all joints, and we believe that the ability to predict the joint moment from the ankle can likely be described by the muscle synergies during gait with muscles in the proximal thigh. We then utilized statistical parametric mapping to evaluate where sonomyographic prediction of joint moment was significantly different than the actual joint moments. As you can see on the bottom row, there are larger regions of significant difference when comparing the ankle joint moment prediction to hip and knee for all walking tasks. And there is a slight region of significant difference at almost every single joint just before swing phase of gait, which we find very interesting. In conclusion, sonomyography can be used to continuously and accurately estimate multiple inputs for potential control of assistive devices, and future directions will include subjects with lower limb amputations, more complex movements, and the evaluation of A-mode ultrasound sensing, as well as integration with assistive devices. Thank you for your time, and here are some references.